Imagine a massive national infrastructure project. You need to plot a brand new high-speed rail line across 3,000 miles of diverse terrain. The first major hurdle is entirely physical. Engineers have to find a path of least resistance through dense mountain ranges, wide river basins, and steep valleys. Then they hit the hidden hurdles. They have to navigate invisible boundaries like protected environmental zones, local zoning regulations, and a maze of existing subterranean utility lines. But during the planning phase, a fatal flaw emerges. The engineers do not have a single unified map showing all of these obstacles. Instead, they have dozens of disparate, uncoordinated maps from different sources. Designing and managing modern physical space becomes impossible when the maps themselves refuse to align. Historically, government agencies operate as isolated islands, with each department collecting and storing its own geographic data independently. The environmental agency might plot their floodplains using one specific software standard and projection scale. Meanwhile, the Department of Transportation draws up their highway grids using a completely different, mathematically incompatible coordinate system. Look at this diagram showing what happens when a planner tries to put these two datasets together. The grids fail to align, and the highway bridges completely miss the rivers they are supposed to cross. This is a data silo. In the real world, this mismatch causes months of bureaucratic delays and millions of dollars in costs just to manually translate data from one system to another. To fix this chaos, planners rely on a centralized single source of truth known as the National Geoportal. When every agency uses a different digital language, the simple act of sharing information becomes a structural barrier to any large-scale project. To understand how the geoportal solves this, we have to look at the scale of an entire nation's geographic boundaries. The foundational layer of the geoportal relies on raw, standardized topographical and climatic data covering the whole country. The core mechanism here is interoperability. Rather than working in isolation, different government agencies plug their live, continually updating data directly into this shared foundation. This minimalist outline is our baseline canvas. First, environmental layers of rivers and lakes drop and lock to the geography. Next, standardized highway networks drop in, aligning bridges exactly over water. Finally, forestry adds zones for forest fire risks. By stacking these layers on a single standard, new insights emerge immediately. Emergency planners can now pinpoint the exact highway evacuation route that is threatened by a flash flood and a forest fire at the same time. Stacking these data layers allows planners to spot hazards, like those overlapping fire and flood risks, before they become emergencies. And this system scales all the way down. If we zoom in from those regional networks, we reach the micro level of a single city block. This highly granular data is formatted as an open standard for public use, rather than being locked behind restricted government firewalls. Commercial developers tap directly into the geoportal's live data stream using a secure digital pipeline called an Application Programming Interface, or API. A logistics company, for example, can call live traffic, precise elevation data, and local zoning, optimizing last-mile delivery routes. At the same time, an independent urban planner can query the portal to locate active subterranean utility lines before signing off on a new housing permit. At this local level, the geoportal functions as a public utility that drives economic efficiency. Let's reverse that perspective. Zooming out from the local city block, past the regional highways, we return to the macro view of the entire nation. This system functions as a mirror, updating in real time as survey teams, satellites, and sensors report changes in the physical landscape. This massive visualization shows the aggregate of millions of individual data nodes. This is a digital twin, a virtual replica of the physical country. With a digital twin, a nation can simulate natural disasters, test complex zoning policies, and predict economic outcomes in a virtual environment before spending money in reality. Historically, maps were static, two-dimensional pieces of paper used for navigation. This map serves as a digital framework, providing the coordinates and constraints used to build every road, bridge, and housing development in the country.